Hi folks, today let's solve LeetCode 300, longest increase in subsequence. If you haven't read this problem, you can spend some time reading it. So the question is, given an integer array, we need to return the length of the longest strictly increasing subsequence. So the first example, the longest subsequence can be 2, 3, 7, 1, 1, and it also can be 2, 3, 7, 18. For the second one, it can be 0, 1, 2, 3. For the third one, it's 7. Okay, so how to solve it? We can use dp. So for each dp, the meaning is for each I, if we make that element at the last, like what's the longest subsequence can be. For example, the first element is 10, so we only have one element. So the longest one is 1. The second element is 9. The longest is also 1, since 9 is smaller than 10, so it cannot be increasing subsequence. For 2, it's same. Now we have 5. What we can do is we iterate every element before 5, and we try to append 5 to that element, and we can get the longest one. For example, if we append 5 after 2, we can get the longest one, which is 1 plus 1 is 2. Next, we have 3. We also iterate every element before 3. We find if we append 3 after 2, we can get the longest one, which is 2. Now we have 7. We also iterate every element before 7. We find if we append 7 after 3, we can get the longest one, which is 2 plus 1, 3. Next is 1, 1. We also iterate every element before 1, 1. And we find if we append 1, 1 after 7, we can get the longest increasing subsequence, which is 4. Same for 18. We can append 18 after 7. We can also get 4. So the answer is 4. The time complexity is O(n) squared, and the space complexity is O(n). Okay, now let's implement it. Okay. We need a vector of dp. Then we can just for loop each element. We have a temp. We initialize it to 1, since one element itself can be a subsequence. If nums I is greater than nums j, okay, then we can j plus 1. Okay. Initialize answer. Answer is maximum. Answer temp. And the dp I is temp. Finally, we can return answer. Okay. Let's see what's wrong. Answer is maximum. Answer temp. Okay, we need to initialize the dp array. Let's see. Yes, here it should be dp. Okay. Okay, now let's see how can we improve it. Previously, we need an n square. Let's see how we can use binary search here. The main idea here is we can maintain an optimal structure. Let's say example, the first element is 10, so we can put 10 into our optimal structure. The next element is 9. 9 is better than 10, so we can replace 10 with 9. Since, for example, if there is another 10 after 9, we can construct 9, 10. So we can use 10. So we can use 9 to replace 10 here. The next element is 2, and we can do the same. We can use U2 to replace 9. We get a better and optimal structure. The next element is 5. We just push back the element. After 5, we have 3. We can use 3 to replace 5, so we get a better structure. Since imagine that there is some element like 4, 5 after 3. Now we use 3 to replace 5, then we met 4. Then we can append 4 after 3. Next, we have 7. We can append 7 to this optimal structure. Next, we have 1, 1. Okay, the last element is 18. We can use 18 to replace 1, 1. Imagine that maybe there are 19, 20 after 18. As long as we use 18 to replace 1, 1, we can append 19, 20 after 18. So for each iteration, we use binary search to find the element that is greater or equal than the current element. And we can replace that value with current element if we find such value. Otherwise, we just push back the element. Let's see how to implement it. Okay, here, let's do this. We have optimal structure. Finally, we just return optimal structure size. Okay, for loop. We use low bound to do binary search here. Okay, if we cannot find it, if we find some element, we just make it a better structure. We use num to replace the existing value in my optimal structure. Otherwise, I just push back the value. Okay, let's see. Nice. Yes. So the main idea here is we can maintain an optimal structure, and for each new element, we try to make our optimal structure better. If the new element is very large, we just append it to current optimal structure. If the new element is not very large, in the binary search, we can find the element like greater or equal than the current element, and we can replace the element with the current element so that we can make our structure better. Yes, that's it. Thanks.